our final presentation about subsea Hyperloop. Here was our schedule. Before for our midterm presentation, we choose evaluated the different possible structure for our subsea tunnel, and we have evaluated also the energy required for that. And for today, it's going to be the choose of the design of the structure by itself, and discuss about the way of getting that energy for the Hyperloop, subsea Hyperloop. Here our table of content. First, I will do the introduction. We separated it into 4 parts. So first, reminder of why we want to do this. As you know, carbon neutrality is one of our major highest priority in our world right now. There is a lot of major governments who want to be carbon neutral by 2050. And to overcome that, we need to solve one of the issues that we have is transportation. It represents approximately like 29% of carbon emission right now. And we also need to solve the fossil energy depletion that we mostly use as a fuel for cargo shipping and airplane. The question of why we choose Hyperloop system for that solving that transportation issue is because like it's ultra high speed transportation system with a maximum speed of 1,200 kilometers per hour. It can be an eco-friendly solution since it's only rely on electricity. If we manage to have like renewable electricity power, it can be more green. It's also highly efficient since it's on magnetized track to move frictionless into a vacuum sealed tunnel. It doesn't lose a lot of energy from the friction. So Hyperloop can probably bypass the loading and unloading bottleneck of ports and airports with that technology. It can have a huge benefit in terms of reducing sulfur dioxide created by cargo ship, and also greenhouse gas like carbon dioxide as well. So now let's discuss why we choose Japan and South Korea junction to that project. The distance from Busan to Fukuoka for this project is only 280 kilometers, relatively small for two countries like that. With Hyperloop speed of like 1,000 kilometers, it can be done in only 30 minutes. We need to make it work with renewable energy to make it green as well. There is a potential market of over $65 billion for freight in terms of import and export between those two countries and per year. And there is also like 20,000 people of daily commutes between those two countries as well. There is a cost per kilometer of Hyperloop for onshore. It's different for offshore, like they haven't did any calculation for that yet, but it's approximately $60 million per kilometer. If we compare that with the reality, for example, the double tunnel costed $15 billion, and if you do like 480 kilometers of that, it's only 30. Of course, it's going to cost much higher since we're going to do offshore with renewable energy power plants, but still, for a matter of comparison, I think it's good to see. So to summarize, our objective is to build the Hyperloop between Korea and Japan, to design a tunnel structure between those two countries as well to make it work, and to make it only work with renewable energy for that. So now we are going to talk about the tunnel structure. Just before, on our last presentation, we presented to you 3 possible structures: the submerged floating tunnel, the IMS tunnel, and the road tunnel. They have some advantages and disadvantages. One of the main advantages for water tunnel is like no restriction about operating on the ocean. Like the ship or the submarine can always go past of that. One of the main disadvantages is like it can be a very long tunnel in deep sea. For the IMS one, the same speed of construction is quite high since we just drop like concrete into the ocean, but it can be a risk of sinking ship or anchor ship breaks that the tunnel. That can be a safety issue. For the submerged floating tunnel, there is a possibility of construction in all kinds of sea, in very deep water as well. But it's also kind of vulnerable against ships and anchors as well. So we did a matrix decision between these three kind of tunnel. We found out that the submerged floating tunnel will work the best for our projects. So that's why we're going to use that one for our Hyperloop. So the next question when we choose a structure is like to question ourselves how to design that. So we need to think about different points like stabilizing tension cable, structure of the tube, the material we're going to choose for the density so it can still be buoyant, and the thickness of the shell tube, the joint between the section to make it safer in case of like leaks or something like that. So now we're going to talk about the renewable energy to that. So in the previous presentation, we saw that for 280 kilometers to Japan to Korea, we need approximately 300 to 350 megawatts per day for passenger transportation and 1,100 megawatts per day for freight. So it's a total of like 1,400 megawatts that we need to find daily to make the Hyperloop work. For now, there is various possibility of getting that power, tidal energy, wave energy, wind energy, and solar energy. We'll discuss about those energy just after. First, about the tidal energy. Tidal energy consists of capturing the kinetic of potential energy of the ocean with the tide and generating power from it, like for the with the use of turbine like hydroelectric power plant. But there is a lot of different ways to capture that tidal energy. The most common and the most used one right now is the tidal barrage. It just captures the potential energy of the tidal level between like high up tide and down tide. For example, there is a project in South Korea in Team1 barrage capture like we have a capacity of 540 gigawatts per year of production. But the main issue with that tidal barrage is like highly dependent on the environment where it's located, and it can be placed everywhere in the world. Like it's a specific location that we can put that. So to counter that constraint, we have the tidal lagoon. We create an artificial lagoon with a U-shaped retaining wall like this. And we use like the tidal barrage, the potential energy of the tide level. For now, there is a big project maybe going to be done in Cardiff, in the United Kingdom, with a theoretical production per year of 5,500 gigawatts. But the main issue of that is like the environmental impact. We need to have a lot of concrete into the lagoon and create like issue with the port or stuff like that. And finally, there is the last one, most new for tidal capturing energy is like tidal stream capturing or tidal turbine. It's kind of work like wind turbine, but underwater. We have, for example, the Triton 6, who can produce 10 megawatts of water just by itself. There is also tidal turbine that can float as well, but the project is not like really convincing for now. The main one is like sinking tidal turbine. It have less constraint than other kind of tidal energy capturing devices, since it can simply buy it onshore and can bring it floating with a ship and just sink it down deep into the ocean and produce the energy like that. After that, we have like the wave energy. pro we generate power using wave energy, where we have potential energy as well. There is also different kind of wave energy generator. The first one is a wave energy converter. This the first one. It uses like the wave movement to make move a pump and create energy like that. There is also a wave energy converter that uses the same kind of system, but we do it mostly on a coastal area. Also, the encode buoy that use also like the wave movements, but use a buoy that move a cable or device like that to make you sort of turbine and generate energy like that. And now there is the offshore floating wind energy. The wind turbine converts the kinetic energy of the wind into mechanical power. The good thing about that kind of energy that we can do large scale farm is possible. We have the knowledge to do that. The floating device can be movable as well if we have more wind to another direction than the other. We can have a high economic with larger scale. And one of the biggest offshore wind turbine can produce right now like 8 to 10 megawatts per device as well. There is, for last, the solar energy. Solar energy like converts the sun energy into an electrical power. It uses a photovoltaic system, converts the sunlight directly to energy. We can also do like for the wind turbine, large farm scale solar power, like here, make it float as well on the water. So now we did our decision matrix about what kind of solution we need to choose. And as you can see, all the options discussed can probably be viable, but they are not viable by itself. Like, for example, solar energy, it's only work during daylight or during good weather. Or wind energy, it's only work, for example, when there is a relative level of wind speed. Tidal energy, it's also work if there is relative undersea current or tidal force. So we may have to think also about battery power, maybe, if we want to capture that over energy and use it later. So we thought about the possibility of combining the different type of power plant and make it work all together. The depth difference between South Korea and the Korean Strait, we can use that to put, like, for example, tidal lagoon or tidal turbine on the path of the Hyperloop. Since the solar panel cannot produce all day, we can use other sources, like I said, the wind turbine or the tidal turbine. They have like the wind turbine and the tidal turbine have a high potential of energy production and a high lifetime against the maintenance and the reparation compared to solar panel as well. So now talking about the result. Here is the result of our intercontinental Hyperloop system. So we have first like the renewable power plant cluster. We regroup like the three technology all together by using energy transmission to the tunnel. Since the tunnel can connect the two countries all together, the renewable energy transmission can be used with the tunnel structure. So we solve the problem of the offshore power plant that we have right now by only installing the Hyperloop that can connect the two countries. If somehow we lack of energy for the Hyperloop, we can always go search that energy to the Korea energy grid or the Japanese energy grid. And if we have another power, we can also give them to the back to the Japan or Korea energy grid as well. So we are not going to waste any kind of energy with that system. We have that offshore tunnel for the Hyperloop, and the ship and the submarine can always sail quite smoothly if we put immerse the Hyperloop tunnel like from 10 to 20 net depths above the ocean, cargo ship can pass it quite easily as well. So to conclude our project, underwater Hyperloop system can be the next generation of intercontinental mobility and transportation. It provides a valid solution to one of our main ecological crisis without taking away the need of transportation in our world. Our projects make use of new options of engineering never seen before in such a scale, like for the submerged floating tunnel. The only realistic project for now is in Norway for only a tunnel of 14 kilometers going to be built in 2050. We use also a combination of different technology, like in a cluster. It can be one of the first steps of like power energy production that we are going to see maybe in the few next year. Yeah. Here, like this assessment results and our references, and I think I'm done. Thank you.
All right. So, question from other members? Okay, I have a question. In this picture, the renewable power plant is connected to directly to Hyperloop system.
Mm-hmm.
Is there no ESS system between that? Do you know ESS?
Yes.
And energy storage system? Because offshore wind power is not.
Yeah, like the battery power stuff like that.
Yeah.
Like I said before, we thought about that kind of stuff maybe to be implemented. Mm-hmm. But since the Hyperloop tunnel is going to be connected to the energy grid of both countries, mm-hmm. we thought that we don't might need that. We can just use the energy grid of the two different countries if we lack energy. Mm-hmm. So we might not need to add batteries or stuff like that between those two junctions. Maybe if it's really large, we can connect it to between the Tsushima Islands. Mm-hmm. But for now, we didn't elaborate too much on that point.
Okay, thank you. Any other? Okay. So the kind of tunnel should be the tunnel density, the whole density should be really similar with the seawater.
It's not obligated to be like seawater, since we are using the floating boiler created by the wind turbine to use as a lift of the tunnel. So we can still use like sort of concrete stuff like that to make the target more safety secure. Doesn't need to be like a high level low density material.
So the main source of the buoyancy is sure solar and wind movement.
Yeah, we can also add other buoyancy device as well if it's not enough.
Does that happen maybe ships gonna be in trouble?
For example, the project in Norway, it's also like that. It's in Kanda Lagoon, and the ship are going to pass by as well. And I think I read there is like really not a big issue, since the structure by itself is really rigid and it can move like kind of flexibility into it. Like there is like some secure movement in it. So I think it might be fine.
Check which number to merge.
This we didn't did it like almost like everything worked together. Like we added like few bricks into each work. We just did all together. I can't say which one did what.
Okay. Other? No. You are saying that renewable energy and also the energy coming from mainland is mixed together, right?
Yes.
And you may need to have a balance or ratio between generated renewable energy and energy coming from mainland.
Yes, it's different voltages.
Including, yes.
Yeah.
How much percentage of energy is used coming from renewable energy side? Or maybe
I mean, it was hard to find like any viable solution for like calculating how much energy we are going to generate, since like most of the renewable energy we are discuss here is like new projects. It's really low for now, but yeah, like for example, for the tidal lagoon and stuff like that, we have like some like, we have some numbers for that. But for the offshore wind turbine tower or especially for the tidal turbine, it's hard to find data on real life projects.
did you calculate the energy consumption of the
For the Hyperloop, yes, we have here. Like, the Department of Energy of United States did a calculation for onshore Hyperloop. Like it's probably going to be the same kind of energy required for us. And they calculated those two numbers. Like a total of 1,400 megawatts if we use freight and passenger transportation.
100 megawatts per day?
Yeah.
And the hourly base can be 70 megawatts something, right?
Yeah, maybe. Yeah.
And you need 7 over 10 megawatt heat power system. Something like that, right? Anyway, you may need to try to make a calculation of balance of sources. And also, together with the mixing of direct current to alternating current is another problem, right? So you need to have a convergence.
Yeah, converter system. Yeah.
You also need to consider this one. And my final question is about the submerged depth of the tunnel. Do you have any number there? Because you are saying the ship is passing and also someone is passing under the tunnel.
Yeah.
So there should be optimal submerged depth of the tunnel itself.
Yeah, for that, I think you didn't elaborate too much for that. Maybe I can look at the Norway project.
Right. The Norway project has similar consideration.
Yeah. It's almost like the same kind of submerged tunnel. So you just need to look how much depth or how they did the calculation for that.
All right. Thank you very much. We are